Hi, my name is Alyssa White, and I'm going to be doing my combined spectral problem. All right, so here we're going to be talking about a combined spectral problem for C10H12O. First, what we want to do is to discover the degree of unsaturation, and we calculate that using the formula as we see here, where it's 2 times the number of carbons plus 2 plus any nitrogens minus the hydrogens minus the halogens and divided by 2. We see that the degree of unsaturation using that formula is going to be 5. 5 degrees of unsaturation is often associated with an aromatic benzene ring. And how we can see that is it is 1 degree of unsaturation for the ring itself, 3 for the 3 double bonds that are within that ring, and then 1 more pi bond in the molecule. Most likely that'll be a C double bond O, but we will look further into that. Okay, so the first spectral analysis that we're going to look at is the IR spectral analysis. We're going to start all the way downrange here in the 3100 area. So we see some spikes, and those spikes are indicative of sp2ch stretching. And so those sp2ch stretching are going to most likely be attached to that ring that we identified. Next, we're looking at the 28 to 2900, and that's sp3ch stretching, most likely indicative of some saturated alkyl chains. Next, we'll look at the 27 to 2800 area, and this particular doublet or Fermi doublet is indicative usually of an aldehyde. So now we can kind of see that there's going to be a benzene ring and there's going to be an aldehyde group somewhere. We can kind of get a picture in our mind with that. And we confirm with this at 1700, we see the very common C double bond O for carbonyl, for a carbonyl bond that we thought we might have based off the degrees of unsaturation, and we can confirm it here with the IR spectra. Then down here at 1600 and 1500, we can see this is where usually C double bond C stretching happens, and so that's most likely the C double bonding within the aromatic benzene ring. But so now we know that there's an aldehyde, we know there's a benzene ring, we know that there's some other CH stretching going on, but we need to further elucidate with some other spectra analysis, which we'll do next. So next we'll look at the carbon-13 NMR analysis. That goes from 0 to 200 on this chart here. And we can look first all the way down here at the 195 spike that we see, and that is indicative of a carbonyl carbon. In this area here, between 125 and 155, I know that's a big range, but that is indicative of some C double bond to C within a benzene ring. And then all the way over here, we can see at the 25 to 35, all the way down here is CH groups, likely methyl groups on the substituent. So we were thinking that there was a substituent, that's probably those, and then the carbonyl carbon, and then some double bonding within the ring. So to further explain that, we see 7 total different carbons here. We count 7 spikes. So 7 carbons, and then 10 are within the molecular formula. So that indicates that there's going to be some symmetry in this molecule. Next, the carbonyl carbon is very downfield at 195 because it is connected to the highly polar oxygen. So that brings us to the point of polarity. The closer the carbons are to a highly polar group or atom, the higher the ppm the carbon will be, because in this NMR, they are de-shielded from that NMR magnet. So that's why we're seeing all these carbons up here in the above 100 ppm range, because they are de-shielded due to their being close to highly polar atoms or bonding. So anisotropy, aromatic carbons, and also the C-double are also pushed. They're also pushed downfield due to the altered magnetic field of the circulating pi bonds, which is anisotropy, which that also contributes to the de-shielding. To further elucidate, we're going to have to look at the HNMR analysis as well. Now, to really get a good picture of what this molecule is, we can use the 1H-NMR analysis. We'll start down here at the 10 ppm area. In the 10 ppm area, we see 1H, and that is a singlet. So this is most likely going to be that proton on the aldehyde, which is very de-shielded, so it's a high ppm. It's close to the oxygen, it's all the way out there. Next, we look at these two very similar in ppm, and also they both have two hydrogen. They both are using two hydrogens, and they're also both doublets. So now we can kind of think about the symmetry that we were wondering about on this molecule, and we see one is just slightly higher than the other, and we know that there's a substituent group, and we know that there's an aldehyde group. So likely the aldehyde group is going to be on one side of the ring, and then the substituent group is going to be on the other side of the ring. The aldehyde group is probably more electronegative, so the 7.8 is going to be indicative of these two hydrogens on the benzene ring that are closer to the side of the aldehyde group. And then the other two hydrogens are probably going to be the protons on the ring closer to the other group on the other side of the ring, which we haven't necessarily figured out yet. But here we can now using the HNMR analysis. So we have the 3.0 area right here. We have one hydrogen there, but it is a septet. So this indicates that it is a proton connected. It is a proton on a CH that is going to branch into two CH3s. And so that relates to the septet. Two CH3s has 6 hydrogens, making that septet there. And it's a little bit more de-shielded because it's close to those two groups. Then all the way down at 1.5, we have the 6 hydrogens on those two CH3s. So now we can kind of picture what it actually is when we move on. Okay, so to finally elucidate our molecule, we can see that it will be 4-isopropyl benzaldehyde. So let's double check through all of our spectral analysis if everything's making sense. And so from the IR spectral analysis, we had noticed that there was going to be an aldehyde group, which we see aldehyde group right here. We saw the carbonyl carbon stretching right here. We had also seen that there was going to be some saturated alkyl chains, which we see over here. And the CH, that is the aldehyde CH, all the way over here. Next, from our NMR 13 analysis, we had noticed that there was going to be seven different carbons, but 10 in the actual molecular formula. C10, but 7. So that means that there's going to be some kind of symmetry, which we see as some kind of symmetry, where we have at least these two H groups are the same, these two are the same, and these two are going to be the same, and the C's are going to be the same on each side. So there's some kind of symmetry there. We also noticed that there was the carbonyl carbon, the C double bonds within the benzene ring, and then the methyl group somewhere. And then when we finally looked at our 1H-NMR, we can see all of these things occurring. We see the proton on the aldehyde, which is very de-shielded because it's all the way over here next to this electronegative oxygen. We can see the 7.8 hydrogens, which are slightly higher because they're closer to the aldehyde group. And then these two hydrogens, which we suspected would be closer to the substituent group on the other side. So those are the protons closer to the other group on the other side of the ring there, like we said. And then that 3 is going to be the hydrogen right here that is connected to, because it had a septet, we know that it's going to be connected to the 2 CH3s. So we see that there. And then finally the 1.5 is these 2 CH3s. Their protons connected to the CH3s. And they're doublet because their next door neighbor is this hydrogen right here, making a doublet. So now we have determined that the final outcome is the 4-isopropyl benzaldehyde, and that is my combined spectral problem.